That's what I wanted to hear. All right. We left off here last time. Methods of finding test values. What is a test value? Why do they call it a test value? Because we have to know whether we reject or fail to reject the null hypothesis. So we have to know, we know from the alpha value what our critical value is going to be. That's the critical value is the number that tells us whether at that point, whether if it's above it or below it, whether it's good or bad, or if it's confidence interval. So the first method is really the proportion method. I hesitate to really talk about this because it's not used in the real world. The p-value method is not really used because, I mean, you can't publish with it and you can't really use it in school. So, but we're going to use it anyway. It's the probability of getting a value of the test statistics that is at least as extreme as the test statistic obtained from the sample data. And we'll look at later on p-value, how it relates to whether we keep or reject the null hypothesis. Note, remember these symbols. P is a population proportion and p hat is a sample proportion. Step one, find the area beyond the test statistic, your z-score. So the test statistic that's the value that you're looking for. How do we use the z values, z-scores to find the test statistic? What do you need to find the z-score? Yes, that's how we first started talking about them. But now what do we need? Alpha. We need to know what is our confidence level. You're absolutely correct there. We first calculated, remember the z value was x minus x bar over s. We needed that. But now since we're past that, now we're at samples. Now we say, how confident are we? Now the p-value, that's the test stuff. The z-score gives us the value, the critical value that if it's a left tail test, if our p-value is less than the z-score, then we reject the null hypothesis. If we have a two-tail test and it's either less than or greater than the z values, the critical values, then we reject the null hypothesis. If it's a right tail test, what do you call this area here at both ends or at the end of the tails? What do we call that area? No. Critical region. Yeah, and in these, we can't use outliers. Remember, one of the conditions are we have to have a normally distributed curve with no outliers. So with our p-value, once we know what the critical value is, if our p-value, the test itself, if it falls in the critical region, then we reject the null hypothesis. If it falls outside of it, then we fail to reject the null hypothesis. Now that goes back, what is the null hypothesis? We talked about that last time. Because remember, we have the null hypothesis as opposed to what's this one called? Alternative. What does this one have to have? Or what can it not have? The alternate hypothesis cannot have a what? Equal sign. So it's going to be less than, greater than, or not equal to. Which means the null hypothesis is going to be less than, equal to, greater than to, or equal to. What's the difference with these? if whatever the alternate hypothesis is, wherever if it's a inequality, that tells you that you have a one-tailed left test. If it's greater than, then you have a one-tailed right test. If it's not equal to, then you have a two-tailed test. So this is our alpha, this is alpha over 2, this is alpha over 2. That's the recap of what we've been doing. Everybody caught up now? All right, let's look at now with the critical value method. It seems like we're repeating these things because it is the same stuff over and over. We only have three possibilities. We have the p-value, the critical value, and the confidence interval. So what do we know about the critical value method? With this method, the critical value method of testing hypotheses we make a decision by comparing the test statistic to the critical values. Value or values. And the critical value that separates the critical region from the value of the test statistic. It separates the critical region from the values of the test that leads us to either reject the null hypothesis or fail to reject the null hypothesis. What do the critical values depend on? The null hypothesis, the sampling distribution. Remember, it's got to be normal. And significance. Level, alpha. Because it's important that our distribution has to be normal. And there's a whole bunch of things we're gonna talk about there, which we have talked about. If you have a large enough data set, then it really doesn't matter what kind of numbers you have. I mean, whether you have the population or the sample deviation. But if you have a small number of data sets, you have to make sure you have the population data information. So here's an example. The alpha is 0.05. Find the z-value. Identify the critical region. And the critical value. So how do we find the z-value of this? Which table, Z or T? Yes, typically we use the Z table. When would you use the T table? Hmm? Z can be two-tailed test also. If remember we did earlier, if it's a two-tailed test, then we do this alpha over two. But typically we use Z, and a t-test is, there are two conditions. If we don't know the standard deviation of the population and the sample size is large, or if we do know the standard deviation of the population, the sample size is small. So this one we'll use a Z-test. So what is 0.05? What do we do with that? We only divide by two if it's two-tailed test. So here we're looking at one-tailed test. Right. The first thing we do is 1 minus alpha. And that equals 0.95. What does this number represent? The area under the curve to the left of the z-score. So we have to look for the number 9500. So we look inside here. The closest we can get to 9500 is now here's 9500 is between these two right here. So since it's exactly in the middle of those, we take the average, which is 1.645. This is my z-value. One 1.645. That's my z-value. That's also called the critical value. So the area over here is called what? That's the critical region. This is where the alpha equals 0.05. So everything else below here, that's where the 0.9500 of the rest of the data that exists. So the critical value is my 1.645. My Z value is also 1.645. They're the same thing. Okay. Because you're going to see these terms a lot: critical value, critical region, confidence interval, confidence level. So also alpha determines your confidence level. How sure are you about your data? What we're saying is this, is we're sure that our data is going to be greater than 95% of the other data. Or our final sample will be greater than that. So decisions, decision, I said it was singular. Decision criteria for p-value versus the critical value method. So it's asking you how do we know whether we keep or reject the null hypothesis with respect to these, if we're using the p-value or we use the critical value? So if we're using the p-value, if the p-value is less than or equal to alpha, then reject HO. If your p-value is greater than alpha, then you fail to reject HO. That's if you're using the p-value method. Is there one? Do you have to pick one of the other? No, it's user's choice. We did. We have these already. But yeah, we'll look some more. Because actually, we just did it right here. Now the condition for using this is 1, 2. Using the critical value method. If your test statistic is in the critical region, reject your HO. 2, if the test statistic is not in the critical region. Then fail to reject the null hypothesis. And be very careful about how you say it. You never use the term accept. You never say, I accept the null hypothesis, but you either reject it or you fail to reject it. You don't really necessarily keep it because we don't know enough information whether it's really true or not. It's just that with the information we have so far, this is the best we can say. Now, for the p-value method, there's a little saying that is commonly used in statistics people. This is how you can remember it. If the p is low, the null must go. So if your p-value is less than alpha, then reject it. So if your p is low, the null must go. So we've talked about the p-value and the critical value. Now we have the last of the three methods, the confidence interval method. So confidence intervals for hypothesis testing. Again, what is a confidence interval? It is an estimate of a population parameter that contains the likely value of that parameter. So what is that and how do we do this? So if the critical value, because I mean, as we talked about the P and V values, if the confidence interval does not include the claimed value of a population parameter, then we reject that claim. So the confidence now, okay, that's the confidence interval. Then we look at confidence levels. What is exactly a confidence level? If it's a one-tailed test, or if it's a two-tailed test, what do we call it? What is a tail? When we say one tail, two tail, what does that mean? What is it referring to? Of what? And what's that area called? Yes. A tail is your critical region. How do you determine if it's a one tail or a two tail test? What determines that? The alternate hypothesis determines whether it is a one tail or a two tail test. Because remember, the alternate hypothesis can only have less than, greater than, or not equal to. If it's less than, since it's pointing to the left, it's a one tail left test. If it's greater than, it's pointing to the right, it's a one tail right test. If it's not equal to, then it's a two tail. And that's why when we use this, we use the one minus alpha. This one is the alpha. This one is the alpha over two. So pretty much if it's like a one tail right test, we use a confidence level of one minus alpha. If it's a right tail. On the note package that I gave y'all, we could see about the equivalence methods, how they're equal. I said, also very careful, I put this in there. Caution, in some cases, a conclusion based on a confidence interval may be different from a conclusion based on a hypothesis test. Conclusions based on confidence intervals may be different than those based on hypothesis testing. Why? Why would they be different? Because what is the difference between confidence interval versus hypothesis test? They're both estimates because they're both estimating the population. For hypothesis testing, we have a null and alternate hypothesis, which we determine if it's a one-tail, two-tail test. We know the alpha, the confidence level, alpha. But what is the confidence interval? What does it entail? The only thing that it only uses alpha, nothing else. Because what it's saying, because of this level of confidence, I can give you two values now that will, because once you get the alpha, you determine if it's a one tail or two tail, whether you have to divide it by two or not. And then from there, you find your critical values. Now, this is your interval. So you have A and B. What you're saying is that your population will fall within that interval. So it's a pretty wild guess. You're saying it's all based on your confidence. It changes because if your answer doesn't fit in there I'll say let's say an alpha equals 0.05, let's try something smaller or something wider, or 0.25. You can adjust it until it fits what you're looking for. That's the bad thing about that. But with hypothesis testing, yes, you have your population information, you have your mean variance deviation, you have your confidence level, which you need to create to find the critical value. So let's look at this chart. Here's your parameter. Which we have a proportion. We have the mean. And we have the standard deviation. And if you have a standard deviation, that's either rho or S, then you always find the variance. Is the square of that. Now, what this side's going to look at is a confidence interval equivalent to a hypothesis test. Do they come up with the same conclusion? In proportion, no. Simply because of the way that the proportion is determined. The mean and deviation, yes. So the confidence interval method is equal to the hypothesis testing. Again, because of the information that you're putting into the equation. What about the results? Can errors occur? We had some examples earlier this semester, in earlier this last chapter of this chapter, where remember when we talked about the people taking drug tests and they never used drugs, but they were found to be positive, or they do use drugs and they were found to not use drugs. So mistakes happen. Because of that, we have two different types of error sampling. Errors occur. And besides human error of just not looking at the numbers correctly, some of these happen. Here's two types of errors. The first one is called a type 1 error. And yes, if you do get this, you have to call it, you have to say, we've discovered we have a type 1 error. This one is the mistake of rejecting the null hypothesis when it is actually true. And a type 1 error is referenced as alpha. Not the same alpha as a confidence interval, but when we talk about errors, that's where we use it. So a type 1 error is referred to as an alpha. So an alpha is the probability of a type 1 error, which means rejecting HO when it is true. So if type 1 is alpha, what do you think type 2 is going to be? What's the next letter in the alphabet? Alpha after alpha? Beta. So the type 2 error is referenced to as beta. The type 2 error, which is referred to as a beta error, the mistake of failing to reject the null hypothesis when the null hypothesis was false. So beta equals the type 2 error equals the probability of failing to reject HO when HO is false. So what would that, remember when we did that drug sample testing and people used drugs that weren't flagged? This is how it would look. So these are our possibilities. You have on very top, you have the null hypothesis is true versus it's false. And then on the row headings, row titles, yeah, top one is reject the null hypothesis. The bottom is fail to reject the null hypothesis. So if the HO is true and you reject HO, what happens? What's that? If HO is true and you reject it. Look back at what we just wrote. Yeah, that's a type 1 error. That you reject HO when HO is true. You reject HO when HO is false. Well, that's what it's supposed to be. That's when you're supposed to reject it. If HO is false, you're supposed to reject it. Okay? You fail to reject HO, and HO is true. Well, that's what it's supposed to be. And you fail to reject it when HO is false, that's the type 2. You have to make sure you check your answers before you publish anything when it comes to this. Because now this is the next part of this same topic we were talking about. This is important when we deal with publishing statistical information. There's even a worse thing. P-hacking. P-hacking is cheating to obtain meaningful results. This is happening a lot with professional journals now. There were a couple of professors in major universities whose articles, whose research had to be removed, redacted, because their information was not correct. And what happened there is the universities then got rid of them because they made the schools look bad. So p-hacking is a very, very, very serious offense. What are ways of doing it? One, ways of p-hacking it. Now, let me go to the next page. Because this is going to be a lot of writing. Ways to p-hack. One, when you run your experiment and you get the data and you look at it, if it doesn't show what you want it to show, what will you do? Well, what people do here, one thing to do is repeat the experiment many times only including the cases or tests that provide meaningful information. Meaningful results. Usually, what that usually means is cases with a p-value of less than 0.05 or 0.5, 0.05, 0.05, because that's usually our alpha that we use. Well, so now then the question is, why would, if you run it the first time, why would it have a different result the next time? If it doesn't work, it doesn't work. Why would the results change if you run it many more times? Exactly. The sample you choose, even though you choose, let's say it's 100 students from the college, it's going to be a different group of students. I mean, if that happens, if you run it a couple more times and you get different answers, that right there tells you your whole test is wrong. Take it back and redo it. And then remember, first part of the semester, we said you have to be very careful because running tests and statistical analysis is time consuming and expensive. So when these people run these tests over and over and over and over, they're paying for each time, hoping to get them the correct answers because usually somebody's paying for it. Which is why you can't believe what any advertisement you see on TV, never believe it. Because it's inherently designed to lie to you. Another thing, remove any sample data that causes the p-value to exceed 0.05. Remember, you have to be less than 0.05. Now, if it's not less than 0.05, that means some numbers inside there are making it bad. So what they do is they manipulate the results by changing the data, by moving the data. Get rid of some, and that's another one. Change the results of the data collected. One of my graduate classes, that was what happened all the time. Students want to make their statistical study work, so they make up numbers. Or they were too lazy to go out and get results, so they made up results. Or they paid some, they told us, hey, go back on there and do it a couple more times. That's why, again, statistics itself is not a probability, is not an exact science. That's why true mathematicians look at it with a grain of salt, which is why it really shouldn't be in the field of mathematics. It should be in the field of business. It should be in the field of biology, or whoever's using it for their specific thing. It should be in there because it's just not an honest pure numbers. Another one. Stop sampling or stop collecting samples once your p-value is less than 0.05. Can you think of anything else you can do? Because if you want to know ways of getting around the rules, ask a student. What ways could you think of that'll get you a result that you like? Hmm? Are you right? Not being a random, because that's another thing. First part of the semester, we said you have to have a random sample. And we had a whole bunch of different methods of getting random samples. That's a good one. I didn't think about that one. You could stack the deck and then get your friends to do those results, and or you can go like the medical samples, the dentist mostly, if they want to sell a specific toothpaste, they'll go to a place, a district or area that specifically use that. Or they flood the dentist's offices with a whole bunch of free samples, and then the dentist gives them to the patients. Now the patients, they think, oh, the doctor gave it to me, so it's got to be good. I mean, last, how many of y'all had teeth cleaning not too long ago? Did they give you some, the packet at the end with the toothpaste and everything in it? What kind of toothpaste was it? Was it Sensodyne? Yeah, and they said, do they tell you that's a that's a good toothpaste, or they don't care? They didn't say anything because they can't, because dentists know that all toothpaste is the same. So, yeah, and my dentist, one of them used Colgate, because that's where they had tons of it free. The other one was Sensodyne. So it pretty much what it comes down to, what flavor do you like the best? What's another one? Make up the data. In other words, only survey 20 people and just copy them. Take those 20 and 20 and 20 and 20, and eventually you get what you're looking for. Or after you finish all the results, just put the numbers you want. That is the big thing. That's what a lot of people get their research kicked out and fired from teaching universities, because they just make up numbers. Why? Because no one will think that it's the calculation that's wrong. They'll think your data collection's wrong. So they'll run it and say, hey, what's wrong? How come these numbers are different? Because you don't do it by hand. You use computers to run these things. You send all your data to the computer, hit go, and it prints out the answers. No one ever think the numbers are made up. But so let's look at an example of type 1 and type 2 data. Example 2. Consider the claim that a medical procedure designed to increase the likelihood of a baby girl is effective. So that the probability of a baby girl is given the following null and alternate hypotheses. Describe a type 1 error and a type 2 error. With this information. So the original claim, bless you, that will be addressed in the final conclusion. All right. So we have this. Remember, the claim is that. So here's our claim. What would a type 1 error be?
Null hypothesis would be that it makes me do, right?
Are you saying for
Procedure makes me do.
no, the null, remember the null hypothesis. Are you talking about a type 1 for a type 1 error?
Null hypothesis, so they're claiming.
Oh, right. Yeah, I should say, yeah, in general, we're null hypothesis, yes.
Procedure, it's like more than 50-50 that you have.
That's the alternate hypothesis. That's what's being claimed. The null hypothesis, it's 50-50. Yeah.
You reject the null hypothesis, even though really it's only a 50-50 chance.
Right.
That's
That's type 1 error, right? Because you reject the hypothesis even though it's true. So yeah, so we reject this. We're saying, oh, that's true. No, so you're rejecting it, saying no. There's something influencing it. So here this is for an alpha test. So is it possible to make the birth rate higher than 50-50 for boys and girls? Has it been tried? Yeah. Well, that's their claim. Yeah, that's again, and then they're gonna come up with this information, their research data that says, "Well, look, it worked. It works." And there you have the p-hack stuff. How would you do a type 2 error, a beta? Remember, a type 2 is you fail to reject it even though it's false. Remember, it says they're finding out that the value is true here. So if that's true, then the null hypothesis is false. If P is greater than 0.05, then the null hypothesis is false. And you fail to reject the HO. The last thing we're going to talk about. The power. Here's the definition. The power of a hypothesis a hypothesis is the probability of 1 minus beta of rejecting a false claim. The power of a hypothesis is the probability 1 minus beta of rejecting a false null hypothesis. So here's an example. Consider the preliminary results that we had earlier. So there are 13 girls among 14 babies born. The couples using XOR. If we want to test the claim that girls more likely, or our P is greater than 0.05, with the XOR method. We have the following null and alternate hypothesis. So what's the, remember, what would this be? Would that be the null of the alternate hypothesis? Why? And yeah, it doesn't have equals. So out of the two, it's the alternate hypothesis. What kind of test is it? The graph. One tail right test. So what would the null hypothesis be? Why do we not put less than or equal to on that one? Because ideally, what's the probability of getting a boy or girl? Same as flipping a coin, 50-50. If you say less than or equal to 50, then you're saying that there's a chance to control what happens. So your null hypothesis has to be exactly 50% chance. You cannot include the less than part. Because if it's less than, then it can be greater than. Use alpha equals 0.05. Okay. Use that. Find the values of power corresponding to 0.6, 0.7, 0.8, and 0.9. These are my p-values, the probabilities. All right. Now, in order to use this method, we have to have technology or charts. So the alternative value of P, which is what we're looking for, 0.6, 0.7, 0.8, 0.9. We calculate the the beta value. We don't have the charts or the software, so these are stated. I guess I need this one. So what's the formula for the power? One minus beta. So the probability of the power for 0.06 is 1 minus 0.06. I mean, not 0.06, is 1 minus 0.820, which is equal to 0.180. 1 minus 0.564 is 0.436. 1 minus 0.227. 0.773. And 0.988. So those are the corresponding values for the powers of those. Now, the question is, why did we use these? And why 0.6789? Why not? What did it say? It said,
That was the problem.
it said because P is greater than 0.5. What's greater than 0.5? And 1.0. Why can't we use 1.0? Well, if it was 1.0, then we get 0. So it wouldn't give us anything. So that's how we do it. Let's see if I have any more examples here. So, all right, everybody. Go and hunt Easter eggs. And let me show you where we are in this